Hey everyone, welcome back and let's start off today's lecture. So the problem that we will be discussing today is from linked list section. Let me just check if you guys are able to see my screen. Give me a moment. Yes, we are live. So starting off with this problem, which is remove loop in a linked list. So for this problem, I'd suggest you one prerequisite is that you must have gone through yesterday's problem, that is to detect loop in a linked list, and after that only try to come up with this video if you're not able to do it on your own. Okay, so let's start with this. You're given a linked list of n nodes such that it may contain a loop. Okay, I'll explain how looping is given in this. It's almost similar to the previous problem. An extra thing, the only difference between the last problem and this is, in previous problem you had to detect loop. Here you have to remove the loop. Okay, so remove the loop from the linked list. If it is present, that is unlink the last node. So if I talk about this problem, at x equal to 2, consider that indexing is starting from 1. So at x equal to 2 there is a loop, right? So you have to remove that loop. For that you need to convert this into a singly linked list that does not contain any loop. So 4's next should not be 3, 4's next should be null. That's how you need to do. So let me just show you now what we are exactly going to do in this problem. Okay, so for example, 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4, 4 is pointing to 5, 5 is pointing to 6, right? And let's say 6 is pointing to 3. For example, this is the kind of linked list given. So first thing is, in order to remove, you want to remove this link. So to remove this link, this 6 should be pointing to null. So it will become, and this link will be removed. So if we want that, we will have to first detect, since the question is that it may contain a loop. If it does, you have to remove it. So first possibility could be that it does not have a loop at all. So for that, what things you need to do in this problem is, first you need to detect whether a loop is present or not. Okay, so once you have detected the loop, then you have to find out at which node that loop is present. Find that node at which loop is present. Okay, so in this case it's 3. So actually basically we know that at 3 loop is present, but ideally what you should have the address of the last node which is pointing to 3, so that its next could be null. So find that node at which loop is present. So typically by this I mean that you have to precisely find the one node previous to that node where loop is present, then you can remove the link. Okay, then remove node. So typically these things you have to do. So talking about first step, you have to go back to your previous problem that we discussed yesterday. So how we did, we used Floyd's cycle detection algorithm. In that algorithm, I'll once again tell you. So we used to have one slow pointer, other one as fast pointer. Slow pointer moves by speed of 1x. That means for every iteration, slow goes to the next pointer and fast goes to next dot next. So fast will be here. In the next iteration, slow comes here and fast goes here, right? And its explanation logic why everything will be there in the last video. So that is why I'm highly suggesting, if you're not aware of this first step, then these will be useless. Okay, then in the next iteration, when slow is here, your fast will move to next dot next, which is this. Next iteration, slow will come here, fast will come directly here. So the moment they meet each other at the same node, that means there is a loop. So one thing has been determined, that loop is present. Now if loop is present, this statement is true, loop is there. Okay, then you have to take further step. Now you know slow and fast pointer must be pointing at the same node, but that node need not to be the node at which the loop actually exists, right? So for that, the next step that you are going to do is, let me just erase this thing. So now you have pointers, slow pointer and fast pointer, pointing to the same node. Do one thing, bring one of the pointers, or you can take a new pointer altogether, pointing to head. Let's say this is your temp node. Temp node is pointing to head, and let one more node be there. That's completely okay. You can reuse these nodes. Now we do not have any use of them. Or you can take another node. So let's take one new node. Let's say current, or let it be slow only. Fine. Okay. So your slow is still pointing to the node at which slow and fast pointer met each other, and you have brought your temp directly to the head node of your linked list. Now what we are going to do, until your temp meets your slow pointer, you are going to run the loop in which temp will be moving to the next node and slow will be moving to the next node one by one. So let's see how they are going to meet, and the node at which they meet is exactly the node where your whole loop is present. So see, for the next iteration, temp will come here and your slow will move from here to here, right? Next iteration, temp will come here and slow will come here. So one thing is for sure, after doing all this, when we brought our temp to head node and then made this iteration until temp points to the same node as slow, one thing is ensured that the moment they meet at the same node, that node itself is the node at which your loop exists, right? Now once you have the pointer pointing to the just previous node, you can mark 6 means this node's dot next as null and node will be removed. So on that thing will come in the later point in time. Now first thing is for you to understand, I'm sure this must be something that you must be wondering, that how is it always possible that at every point, every time, whenever temp meets slow, it is going to be that node at which this loop is present. So to give that proof of concept, let me just tell you again, that's Freud algorithm. Have a look here. So how is this thing ensured? Look, try to understand it in this way. You have a path like this, okay? So you have nodes like this, node 1, node 2, node 3, then you have node 4, node 5, node 6, and let's say node 7. Fine. So like this, these are pointing to each other. This is a circular loop and this is a straight path. Now the thing is, we are bringing our slow pointer, we are making our slow pointer move by speed of 1x and fast pointer move by speed of 2x, right? So whenever they meet, we can say slow must have moved by some distance which is twice as distance of fast pointer. Got it? So it is something like this, that 2 times of the distance traveled by slow, I can write it like this, will be equal to the distance traveled by fast pointer, right? Because fast pointer speed is exactly twice as of slow pointer, right? So let me define for you. This is your path, let's say A. This path is, let's say, slow and fast pointer meet here, right? I'm talking about detecting loop, starting right from the first step. So this path be defined by B. The distance, this distance starting from head till the point where your loop begins is distance A. Then from here till the point where slow and fast pointer meet each other, let it be B, okay? I'm not sure if they meet here only. Let me check. Slow, fast, slow here, fast here, slow here, fast here, fast here, slow here, slow here. Let me check. And let this path be C, okay? 1 2 1 2, for example. Now what you have to do is, you need to determine a relation between these paths so that we can prove that whatever this path is, it is going to have some integral relation with this path. Getting my point? Either it can be equal to it, or maybe it can be twice, thrice, or any times. But one thing is for sure, that no matter how much distance we travel from here to here, this is constant. But in your loop, if you are present here, no matter how many loops you take, you are always going to meet with the pointer moving from here till here with the pointer which we started from here, okay? That's what we are going to prove. So see, this is 2 times distance traveled by slow pointer. Let's say it is a plus, we don't know how many times this loop was covered, so let it be twice of a plus, what is it, b plus c, how many times we don't know, let it be m into b plus c. B plus c is the number of loops that slow pointer must have taken to cover in order to meet with fast pointer. So it will be b plus c. Now finally, let's say it is meeting here, so one more b will be added, right? So this expression should be equal to the distance traveled by fast pointer, which is, again, it travels a, plus how many times it covers this loop, we don't know, let it be n times b plus c, right? N times b plus c, and then plus b, the same thing. Okay, so if we see, it should come something like this. Let us have a look. So a plus a, you can check it like this. So a plus 2m minus n b plus c plus b equals 0. So it should something be like this, a plus b, it should become how much, a plus 2m plus 1 b some minus nc. Let's see how much it comes out to be. Wait, let me reorganize it in this way. 2m, what is the relation between, see, we want to define relationship between a plus b and a plus b, and then this c, basically b plus c. Let's see, so let it be like this, 2m minus n b plus c plus b plus a. Fine. Now b plus c, let it be like this, a plus b equal to, you can manipulate it yourself and it should come out something like this. See, what I'm trying to define here is that the distance that will be traveled by a, right, that will be some integral of this b plus c, right? And how, no matter how many loops we take, this a and c are related to each other in this way, that a can be lambda times c, where lambda is some integer 1 2 3. There is a possibility in this case a is equal to c. There is a possibility, if let's say a is greater than c, right, this distance is greater than c, then it will be in some integral multiple only. Right now, for example, let's say this distance is, how many nodes are there, 2. So if I have to travel this distance in such a way, it would be that a will be some integral multiple of c only, right? So that is what you can define from this expression. Okay, so this is the proof of concept behind it. Now let's move to our code part. Coming on to the code, what we are going to do, we are going to write the detect loop. Okay, detect loop is exactly what we did in the last class. And then the extra thing that we are going to do is, whenever we find a node, the node at which slow and fast pointer meet each other, right? There is a node at which slow and fast pointer meet each other. So you take your new node temp and make it point to the head node. Okay, then you start your loop where head is pointing to head.next and slow is pointing to slow.next. The moment they meet, that means that is the intersection point. Now there is one more case that you should be taking care, and this case, when you try to do it on your own, you will realize that a test case like this will fail. And then you will understand that you have to handle this case as well. What is this case? For example, you have a linked list like this, in which the entire linked list itself is a loop, right? The head node itself is a loop. So in that case, the solution that we are going to write, we are going to add a line of code in which we will ensure if slow and fast pointer meeting at head itself, that means that node itself is a head, and if you try to do the same thing in order to retrieve the last node, tail node, then that wouldn't work, which I will show you while I will be writing the code. So for that, just one extra thing we will do in order to handle this case. So just keep in mind that we have to handle this case as well. Now let's move to the code. I'll code right in front of you, then we will come back and do a dry run to help you understand how we handle the cases that we discussed. Okay, so let me start it off. Fine. So I will first write the detect loop code, exactly what we did in the previous question. So public, and I'll be passing a return type as node, public static node detect. Okay, detect node head. Okay, how do you detect? You take a node slow pointing to head, you take a node fast pointing to head, then you take a loop until your slow is not equal to null, your fast is not equal to null, and fast dot next is not equal to null as well. You're moving slow by a speed of 1x, slow dot next, and fast by speed of fast dot next dot next. Fine. If they happen to meet, if slow equals fast, that means you are going to return that slow node itself. Otherwise, you come out of this loop and return null. That means there was no such node found at which loop is present. That means there is no loop. Okay. Now, how is your return? See, what is it? The return type of this problem? You see void. Actually, what will be happening if you were able to successfully remove the node, the loop, then output will be 1. That will be handled by the function that has been already taken care. And if you're not able to return, means remove the loop, it will return 0. So 1 or 0 will be helping you to know if you have written the code correct or not. Now coming on remove loop function. So first thing, I am going to take node, you can say node found equal, I'm making a call to detect function where I'm passing head. Now if a loop was found, then I am passing slow node. So slow node is the node where slow and fast pointer meet each other. If there is no loop, it will return me null. So one thing that I am going to ask, if this found node is equal to null, then from here itself you just return. Okay, and if not, then you start doing your task. Now the next task that I'm going to do is that you are going to node temp, okay, which I'm making the node temp, I'll be pointing it to head node. As you might be remembering what we discussed, I'll make it point to head node, so that now wherever slow and fast met, the distance from there till the meeting point will be in relation to each other in such a way that this distance will be some integral multiple of this distance traveled. So they are always going to meet at the intersection point at which the loop exists, right? Now one thing that I'm going to take care here is that if this thing I'll write later on. First let me write now while your temp dot next, okay, is not equal to found dot next. Why I'm doing so, let me just tell you, give me a moment. You are going to bring your temp to the next pointer and your found to its next pointer. Fine. Now wait, see, then you will make your found dot next equal to null. That's how you have removed the loop. Now see, what I wanted to do is, if I made this loop go until temp is equal to found. For example, I wanted, actually if I had written it in this way, that temp, while temp is not equal to found, so it would have run a loop in which it will break the loop when temp and found both are pointing to 3. But what I have done is that when the temp pointer itself is just one step before meeting with found, and that is the point where loop exists, just break the loop so that I have the address of this found pointer. Found pointer must be pointing to this node, which is this 4 node, right? So I want the loop to break right there, so that itself at this point itself I can make force next point to null and I can do my task, right? This is the reason, instead of taking another new variable, new pointer by previous and then keeping track of a previous node, I've just put a break here, that the moment they are going to meet each other at the node where the loop exists, just stop before, right before that. Okay, so my found pointer will be pointing to the node right before the node at which loop exists, so that you can make found dot next equal to null. Now this is fine, this will work for the cases, but for the case where your loop is found right at the head node itself, for that it will fail. Why? Because see, you are making your temp point to head node, and found is, you are assuming that found is pointing to some node which is not a head node. Let me just show you here. See what will happen if we continue to use that loop for the cases like this. What is the issue that is going to come? That see, slow and fast pointer are anyway going to meet here only. Why? Let's try. Slow here, fast here. Next iteration, slow here, okay, and fast comes here. Next iteration, slow here, fast here. Next iteration, slow here, fast here. Next iteration, slow here and fast here. Next iteration, slow here, fast here. Next iteration, slow here and fast here. So see, now according to the loop that we have written while, first of all we are taking a temp which is pointing to head. So now my temp is pointing here and my slow is already present at head. Now what I am doing, while temp dot next is not equal to slow dot next, okay, I am doing temp dot next and slow dot next. The problem here is that, see, your slow is also pointing at head, your temp is also pointing at head. Now we are basically, slow here is found, okay, you can take it as found. So you are going to do temp dot next, slow dot next. At every time you will see that they are going to meet only. For the next iteration you will check, if you do a temp dot next and do the slow dot next, they are going to meet at the same pointer itself. So basically this loop will not run. Why? Because their dot next are going to be same only. So in that case, when you do us in the loop, what we have written, while temp dot next is not equal to, after coming out of the loop, you are doing found dot next equal to null, which is slow. So do you want one dot next as null? No. That is the reason this loop will fail for cases like these. So in that, just before going to this loop, do a check if when you bring temp to head, is it still pointing to the same node as slow pointer or the found pointer? If that is the case, that means they both met each other at the head node itself, right? So just do one thing, bring your temp pointer, make your temp pointer move by one step until its next is equal to slow, and then you will get the address of the tail node, and tail nodes dot next will become null. That's what we are going to do in the extra loop that we are going to write here. I hope you all understood this thing. So this was your temp head. Fine, this was your temp head. Here we are going to check if temp, we have made temp point to head. Now is it still equal to the node, means is it still pointing to the node at which your slow pointer or found pointer is present? If temp is equal to found, that means they both are pointing at head node itself. That is when you are going to take this decision. While temp dot next is not equal to head also, you can say, or is not equal to found pointer, both will be correct. You do a temp equal to temp dot next. We are doing this thing to get the address of the tail node, and once you are done with this, bring your temp dot next to null. That's how you will be removing the loop and also return from here itself. Let's try. That's all about it, guys. So we are done with this problem. You can have a look here. Now you can see that we have not used any extra space, as discussed in the previous lecture. Also, there is the hash map method which could have done this obviously a little faster, very small by small difference, but we were using an extra space of maximum big O of n space complexity. So it is, this approach would be a better one in which we are not using any extra space. Okay, so that is all about this problem. If you have any doubts, you can ask me. Let me check. So the app I'm using is OneNote to write on screen. Sorry, OpenBoard. Fine guys, then if there are no doubts, we will wrap it up. Try to solve this problem on your own. First, try to understand the logic behind this. Try to code it on your own. Then try to handle the case that I just put forth just now. And yeah, that's all. Then see you all in the next lecture, that is tomorrow. Thank you and take care.